Good afternoon. This talk is outside the usual range of the talks here. It's partly about microarchitecture and the design of chips, and it's partly about the exploits, in particular the so-called Spectre exploit. Those of you who have any real expertise in either microarchitecture or Spectre will realize that I am grossly oversimplifying for a more general audience and in fact lying through my teeth. But I'd be more than happy to go to it in greater detail, and at the end of the talk there's URLs to some places where you can in fact get a whole lot more of the details if you wish. Now this is actually a story, and the story of course has characters, and all good stories have to have a villain. So as this is dealing with exploits and the bad guys coming in and stealing secrets, well, our story has to have a villain, and villains always have a lair that they hang out in. But there are other characters. In particular, there's the ingenue and her residence, and of course, there's the chest which holds the secrets, and the secret itself. Now, our story begins, the secret is located in the chest, and the chest is located in the residence. And if you want to think about this in machine terms, the secret is perhaps a crypto key, and the chest is DRAM or your hard drive, and the residence is the CPU. Now, the villain is the one who wants to acquire the secret, and he's in his lair, which is some other system, sends messages to the ingenue in her residence, asking for favors. Show of hands, how many here have ever either sent or received in your whole life a real live telegram? Wow. He will, in fact, ask for the secret, but of course, she's aware of this, and she'll say no if he does. Our plot, well, the villain is going to try and get the ingenue to open the chest, pull out the secret, and move the secret into her residence. That is, move it up from wherever it's stored into the CPU. And then he's going to attempt to move it to his lair where he can abscond. Part of these steps to open the chest and move the things into the residence is called access. Separately, the steps of moving it from one residence back to the lair is called exfiltration. All exploits involve both sides of this, and many people, and you'll see an awful lot of comment on the web, confuse these two notions, but in fact they're quite distinct, and what has to be done to defend about them is different. Now, to steal a secret, we must first cause the secret owner, the ingenue, to access it and bring it into the CPU, because the villain has got no way, assuming that he does not physically have the machine in his possession, he's got no way to access the disk or memory. To exfiltrate it, he must then force the ingenue to do something with the secret in a way that leaves tracks. The ingenue is not going to let him get at the secret, but if there's tracks, maybe the villain can find out from the tracks what the secret value actually was. You can stop such an attack by blocking the access or the exfiltration. Historically, most of the CPU chips, all the ones in your laptops here and massive servers and what have you, they all permit easy access because that's required to get performance, at least in the traditional microarchitectures. The designers thought that they were safe because they had blocked exfiltration. They didn't care about the access because both steps are required. Unfortunately, Spectre proved them that they were wrong. I'm going to walk you through a particular flavor of Spectre. Spectre actually is a whole family of attacks that work in recognizably similar ways using different aspects of the machine. But this is just one of them. Again, if you want all the details, there's an URL at the end to a very good presentation of the details. We'll assume that ingenue has got some public functions that the villain can call. So, for example, let's assume that this is a public function in the ingenue's code. Now, this code may be a fragment of a normal piece of code that does something completely different. Those things are called gadgets. A point of historical incidence, the plutonium or uranium core inside the atomic bombs dropped on Japan, the core was known by the people in the Manhattan Project as a gadget. And whether there is any historical connection to the use of an exploit gadget in our context, I don't know, but it is interesting. The code may come from a JIT, it may be just something there, doesn't really matter. But it does mean that the villain can call it, and call it with a whole bunch of arguments. And if you look closely at what that code is doing, that argument is being used as a subscript to A1. And consequently, the villain can use absolutely any value as an argument, and will then be able, by subscripting the array, will then be able to access any location in memory. Note, we're talking a C or assembly language here, or even the binary. We're assuming that you're not working at a high-level language. The A sub x will give you any address you want. He still has to get it back, because all that's done is loaded into the ingenue CPU. So the ingenue doesn't want him to be able to force access anywhere. So she tests the arguments and inserts a perfectly ordinary bounce check. If she didn't insert such a bounce check, that's not Spectre. That's just a bug. Now when the villain bangs on it, well, he gets back zeros and zeros and zeros for all the areas outside of the A1 that he's supposed to be being able to get access to through the API that the ingenue is exporting. But when he puts a value as an argument in which is within bounds, he's good, he gets whatever this thing computes. And by putting in the bounce check, the ingenue has blocked him out of everything he's not supposed to be able to get. Maybe. The problem is what's called speculative execution, which is a characteristic of all out-of-order machines, which includes essentially all high-end existing cores. It is not, in fact, something which is done in low-end. The Z80, for example, doesn't do it. How many people have ever programmed for a Z80? Oh, many more than do telegrams. But this is a hardware characteristic. This is not something the compiler does. It's not something the operating system does. It's not something that the ingenue's code does. This is something the hardware does whether you want it or not. A test looks like it does this. First, it compares the bounds, then it branches and possibly returns. Then it does the access of A1 and the access of A2 and whatever else it does. That branch is what would make things safe. Unfortunately, modern hardware doesn't actually do this. What it does is it does the bounds compare, then it does the accesses, and maybe a whole bunch more, and only then does it do the branch and verify that you are, in fact, within bounds. This has been reordered the operations and done them out of order and ahead, and this is why it's called run ahead speculative execution. There's your branch. This is not under the control of the ingenue. As a result of this reordering, the villain can access A1 sub anywhere because we went and did the access before we discovered that we were out of bounds. Speculative execution, well, how do you get from this to this? The branch takes a long time. The loads with the accesses take a long, long, long time in machine terms. And microarchitecture people don't like things that take a long, 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 long time. So the solution that has been developed, initially starting with Thomas Sulu in the 36091 over 50 years ago, but basically the solution is you do them both at once, not necessarily in order, and then figure it out later and after you have all the things in hand. That is the reorder and the speculative execution. The question is, then the hardware know how to try this as opposed to the other? Well, it knows because the last few times that it did this code, the branch did not go to the return. So in the hardware, there's a whole hunk of hardware and gates called the branch predictor that says, what did you do last time? Well, I think you're going to do the same thing next time. And it predicts that the branch will not be taken and lets other things go ahead without actually checking it. The check will happen eventually and everything will get undone. Well, most things will get undone. But it'll start the A1 access right away because it predicts that, in fact, is what it's going to need to do. Of course, you can drive the branch predictor any way you like. If the villain, remember the villain? If the villain keeps sending the same in-bounds value over and over and over and over again, the branch predictor, which is watching what he's doing, will say, oh, I've finally gotten the idea. The next time he does it, he's going to be within bounds and go and do the right thing again. Except he sends one that is not within bounds. And sure enough, the ingenue opens the memory chest there, and more correctly, the speculating hardware has, and we have accessed the secret, even though the access is in fact incorrect. The predictor said, we think we're going to do this. Now, in our story so far, the villain has trained the branch predictor to expect valid input and then is sent invalid. Run-ahead speculating hardware has speculatively executed the predicted access. The secret has now been laid bare, but it's still only in the ingenue's core. Now we have to exfiltrate it back out to the layer. If you remember the ingenue's original code, that part, the access to A1, is for access. This part is for exfiltration. And this is what makes Spectre so deviously clever. You'll see how it works. The villain uses the cache to exfiltrate. By using the secret in an address, you'll note that A1 sub X is the secret, and we're using that secret value as a subscript in another memory reference. And so the secret is now part of the address in the reference to A2. So the secret value is used to calculate the address, and if the secret value is 0, that calculated address will be A2 because it's A2 sub 0. And if the secret value is 1, the calculated address will be A2 plus 64. You notice the times 64 there. And 128, and you get the idea. In terms of cache lines, instead of bytes, if the secret is 0, it'll go to the line that contains A2. If the secret is 1, it'll go to the line, the next line after the line that contains A2, or plus 1 line and plus 2 lines, and so forth. Now, the cache is a two-dimensional array of bytes copied from memory. Caches was the great innovation in the 70s and 80s and essentially what made modern processors be able to do what they do. A typical high-level cache have lines which are typically 64 bytes, although there's an immense amount of variety here. And typically one will contain 512 different lines, or a total of 32 KB. This is merely typical. I recommend the Wikipedia article on caching, which actually does a very good job on it. Now, if the line that you are accessing happens to be one that is in the cache, that is the address you're using is addressing one of the lines in the cache, your access will be fast. This is the whole point behind a cache. If the line addressed is not in cache, we're probably going to go all the way to DRAM, and in machine terms, that is glacial. So, in order to speed everything up, if you access a line that is not in cache, it will be brought in and placed in cache, tossing something else out. This is made use of in the exfiltration. First, the villain repeatedly accesses memory and accesses memory and accesses memory to accesses which are valid in the villain's space, but which will wind up in the different cache lines in the physical cache. So there we go. The villain succeeds in loading 512 of the villain's valid lines into cache, flushing out everything else that had been there. Then he does the access. Now, the effect of that access is the ingenue's hardware will run ahead, picks up the hardware, and for purposes of the slides, say that the secret value is 2. Figures the address of A2 plus 2 lines, runs out to DRAM and gets it, pulls the thing in, and it gets put in the cache. That's the hardware doing it. It's not the program doing it. The expectation of the hardware is that somebody is going to look at something else in this line again and again and again, and having it in the cache will speed the program up, and in general, this is true. Eventually, the hardware figures out the branch predictor was wrong, and everything that it did speculatively gets tossed, and it returns the 0. But not quite everything, because in fact what happens is it leaves the cache changes because it doesn't really have anything else to put in that line, because what was in there before has been thrown away, and who knows, maybe that line will be needed, and so it doesn't bother getting rid of it. Meanwhile, back at the Lair, which is probably an SMT thread that the villain is running, or happens to be on the same cloud machine that the ingenue is running on. When he gets control back, remember it will return a 0 because the access was out of range. The cache now looks like this. All but one of the lines has the value that the villain put in there. One of the lines, which actually contains a secret, but he can't get at because the address is wrong, is different. So the villain proceeds to run through the same set of addresses that he used to fill the cache, looking at each line one at a time, and he measures the time it takes to do the read. Well, when he goes to the first line and does the read, it's fast because that line was in fact in cache, and bingo, here's your response. And again, when he hits it again, but when he gets to the line that has the ingenue's line in it, it's not fast because he's trying to read his line, and that's not what's there. And the hardware will run all the way out to DRAM, and it will take a long, long time compared to the other cache accesses for that value to be brought in. So he measures the times, And he notices that when he read line 2, it was slow, which means that the secret line had to have been the one put in line 2. And you think back about how that address was computed, that means that the secret's value was 2 because that determined what the value got, which line got updated. That is extremely devious. We know the secret value is 2, and exfiltration and access have been accomplished. Exit villain. It turns out that if you, on a conventional modern machine, using this technique, and you want to pull up a 256-byte key, you can do that in 10 milliseconds using this technique from anywhere in the ingenue's address space. Some details. It's a family. All members of the family depend on run-ahead speculation. The exfiltration methods vary, including their effectiveness and how much trouble it is to get everything set up to work right. Again, I refer you to the URL at the end. The hardware speculation is essential for the performance of virtually all high-end microarchitectures produced by many, many vectors. Any machine that does not do run-ahead speculation is immune to Spectre. It may be vulnerable to other things, but the entire Spectre family it will be immune to. The immune ones include most low-end machines. If any 8 or 16-bit machines will not be doing run-ahead speculation, and especially in the embedded world, many of the, even the larger machines do not do speculation. Now, what can you do about it? I mean, you're a hardware vendor. What can you do? To begin with, it is trivially easy to fix Spectre. Just don't do run-ahead. And this is usually a fairly easy thing to do. You reflash the BIOS and flip a bit somewhere in the thing, and it doesn't do speculation anymore. And you will hit a sizable performance penalty on most applications. Now, alternatively, you can add explicit instructions to temporarily shut down speculation in a vulnerable area of code, perhaps bracketing that gadget. You'll still have some performance penalty. And then you're left with the problem of how do you figure out where it is that somebody is going to make that attack and get the software corrections in the right place. Yes, well, good luck with that. You can just use a programming tool that doesn't let speculative values be used in addresses. You still have a performance penalty, but there are at this point, something like 15 or 16 different methods known in the Spectre family to do exfiltration, not involving the cache addressing at all. There is a lot of that been going around for the past year. Fixing it is easy. Just don't do run-ahead. What's hard is how to do run-ahead and get performance. And this is where the microarchitecture comes in. Now, I work with the mill CPU architecture. Who's heard about the mill? We're getting out there, folks. Well, it is very different, and I'm going to show you how we get high performance in a non-run-ahead environment. There are other possible approaches, but the traditional run-ahead is clearly not working, and the Intels and AMDs and ARMs of the world are having to do some very serious rethinking, both architecturally and in the marketplace. A typical memory hierarchy looks vaguely something like this. This is highly abstract and The real world is rather different and has a whole lot of details glossed over here. When we issue a load, the first place that we look is in the top-level cache, and access time for that is typically something around 3 cycles. If we do not find the value in the top-level cache, we go to the next level cache. L2s is typically something 10, maybe 12 cycles. Eventually, we run out of cache, and we go to DRAM, and you're looking at 300 or more. This is why there's caches. This is why there's run-ahead. Memory latency is the reason for speculation. If you can start a load early, then you can be doing the fetch while the core is doing other things. So if I have other stuff, and then I do a load of X, and then I use X, the use being a consumer, then I can get better performance. If I start the load, then I do other stuff, then I end the load, and then I use it. The mill has what is called a deferred load, which explicitly splits the front and back of this. These are actually, in some cases, 2 different operations separated by a fair amount, potentially many, many cycles in time. In other cases, and the one I'll show you here, we just simply say how long we want to wait. Implementation details in that video. There's 20-odd hours worth of detailed architectural videos on our website available for you. Now, the load problem is one that we all face. If you do an add and then a load, and you shift the value, picking stuff out, and then you store it, what you will actually get is the hardware will do the add, and then it'll start the load, and it'll stall, because the load value isn't available to do the shift. And it'll stall, and it'll stall, and then for a change it'll stall, and finally you'll get around to retiring a value to you and doing the shift. And we carry on at that point. Every architecture has to deal with this problem. It is fundamentally when the fact that CPU speeds wound up increasing dramatically over the years, and memory speeds did not keep up with them. Mill deferred loads, the generic mill operation, well, it's a load opcode, and there's the address, which is the usual address stuff for an address format. We say how wide the value that we want to load is, and that's part of the operation. And then we add another unusual argument, which is the delay, the number of cycles that we want to have to wait before the retire becomes available. So if I do a load there and I put 4 in that value, then I can do an instruction, I can do instruction, I can do an instruction, and then finally, 4 cycles later, the load retires. And at that point, I can put to my consumer. Note that the load and 4 cycles of other stuff have overlapped, so that if we actually got the value out of the D1, which takes 3 cycles, that value was already there when the consumer gets around to asking for it, top speed all the way through. The data becomes available at the point of the consumer. When the load issues there, the retire is deferred for the 4 instructions. Now, if we reorder our code, and you talk the compiler into doing it, or your hand assembler, you can rewrite things so that you can separate the loads issue from the loads retire by more. So for example, if this is our code, that hides 1 stall because there's 1 operation in between the load and the consumer. But I can hoist the load over prior operations like that, and now I'm hiding 2 stalls. Similarly, I can lower the consumer over something else down to there. Now I hide 3 stalls, and my access to cache was free. Top-level cache. Again, if we're going to DRAM, everybody's going to be slow mill too. There are constraints to reorder. Obviously, you can't hoist a consumer over its own producer because the data flow has to be preserved. But in addition, producers and consumers have side channels to communicate with each other through other things going on in passing back and forth into memory. Where this is not all happening in core because one producer can have stores intermixed with the loads that it wants to do. But the hardware knows that the addresses that are used are the same, and this is called aliasing and is a fundamental problem in microarchitecture design is what do you do about aliasing? And this is percolated back up into programming languages and such that you can, by adding pragmas or some other feature of a language, assert that an alias is in fact not possible. And the hardware will then the compiler will then happily hoist things up. But in general, the compiler cannot tell whether hoisting is possible over a load, over a store, and must be defensive and assume the worst case. But as a matter of actual practice, true aliasing is very rare in code. And so nearly always when the compiler is being defensive, the compiler is in fact suffering from false aliasing and there was no need to be defensive. It's just the compiler can't tell. I write compilers. Well, in the abstract sense, for all architectures, a load sees memory as of a certain point in time in the sequence of changes that get made to the memory. It sees the effects of stores that happen before that point of time, and it does not see the effect of stores which happen after that point of time. Exactly where that point of time is part of the semantics of the hardware, which again percolates up into the programming language. And sometimes hardware will say, well, we're not really sure whether you can see it or not. And this leads you into the morass that is memory models. On the mill, loads see memory as of the retire of the load. Not as of the issue of the load, but as of the retire of the load. So if the instruction says with a delay of 7, yes, this means don't bother me with the result for 7 cycles and then give me the result, and I can be doing 7 cycles worth of stuff while you're running out trying to get a value for me. But it also means give me a value as it will be 7 cycles from now. As a result, we are immune to aliases because issues now may be hoisted over stores, including those which are true aliases, because that's not the value that the hardware is going to return to you. It's going to return to the value after those stores at the point where the load retires. This is part of the architecture of the mill. It's done in hardware, and you don't have to worry about it. The compiler knows that the memory value will be puts the load in with the memory value so that it will be seeing the right things in the stores. If this was the original code with the retire there, as modified, clear? Same semantics. Same value loaded. This is exactly what the hardware run-ahead is doing, except there's no speculation and no run-ahead, even if the store is the same address. Of course, there's more problems in stores. You also can get in trouble. Take this little fragment here. We can speculatively do this. We load both of them. The pick operators choose one of 2 on the mill. And pick will select one of the 2, and then we use that address in the store. But if we do it like this, well, what happens if P or Q happen to be a null pointer? We're loading both to speculate in order to get performance, but one of these is unnecessary. We don't know which one, and we are potentially oopsing because we're dereferencing a null pointer that, in fact, if we executed the thing in order, we would never, in fact, touch because the B would have protected that. But we're speculating for performance, and we are, in fact, issuing both of them at once. The no-low would default even if it was not used, and we really don't want to do that. The mill solution for this problem is to augment every operand in the core with an extra bit called the not a result or NAR bit in its metadata. This bit is set on every value whenever the operations determine that they cannot produce a valid result. The signed overflow for shifts, loads with null addresses, anything in which, folks, this value is bogus. What you get back is a NAR with the NAR bit set. So if the operation runs to OK, you'll get a perfectly ordinary value with a cleared NAR bit. And if the operation does an oopsie, you will get a NAR which has the NAR bit set, and the remaining values of the operand contain a payload, which one part tells you what it was that went wrong, and one part tells you where it happened, and the debugger does a pretty good job of telling you where the fault happened, not where we discovered that things had gone wrong, but where the fault happened. Now, operations divide into two kinds. A speculable operation has got no side effects, an add, for example. And if it gets in a NAR, it propagates those NARs, so a NAR in will lead to a NAR result, but will not lead to a fault. This is true whether it's a scalar or a vector. The vector, the individual elements of the vector have NAR bits, and so you can do an operation which will propagate the NARs as well as computing the correct results for the other elements. Typical speculatives, mul, add, shift, pick, what have you. A non-speculative operation is something that's got side effects. There's nothing we can do. We can't do the side effects. We don't know whether the value is valid, so we fault. You're now in your fault handler and software, and whatever your host language or runtime system does with that, well, we do hardware microarchitecture, and your runtime system is somebody else's problem. Now, if you compare these different approaches, in order, your Z80, it is immune. If you have anything where you really care about security, this is a very good choice to use. It's slow, it's very low power, extremely economical, and dirt cheap. They're like 7 cents a piece in volume. If you care about security, see if you can find a chip which is in order. A conventional chip using raw run-ahead, the x86s or whatever that's in your laptops, they are unsafe. They are faster. The run-ahead did buy something. The power consumption is extremely high. Out-of-order processing in a microarchitecture is very, very expensive compared to an in-order machine with the same rough capability. If you mitigate that, well, it may be more secure. It will certainly be slower. And the power remains high. If you mitigate it all the way down, you've now spent a whole lot of power to do out of order that you're not using. Mill, immune, faster than the regular chips that you're getting, and low power because it's in order and it does not have to have the out of order logic. We were not designed to be immune to Spectre. The design long predates the discovery of Spectre. Instead, the mill design was to make it simple and transparent. I encourage you to take a look at some of our videos, and you'll see how we went about that and what the result was. We rejected out of hand complex techniques like SMT and run ahead. On the other hand, the next attack, and for sure there are more attacks out there, may hit the mill too. We were just frankly lucky that we were immune to Spectre. On the other hand, being simple and transparent makes it less likely that we will be vulnerable to attacks. Complex tends to make holes. So, the mill protection model, you only see what I give you. I can only see what you give me. The mill is designed for a microkernel OS. Fast and cheap, no third parties. And the basic principle for security, it must be unobtrusive, unavoidable, and cheap. Or it won't be used. And if you see the alternatives that are being offered to you for improving the security in your laptops, cell phones, servers, they're not unobtrusive, they're not unavoidable, and they're very much not cheap. Our little story, some credits. The villain was played by Eric Campbell. If he looks familiar to you, he played the father of the girl or the policeman in many of the Charlie Chaplin shorts. The Lair, of course, is not revealed, although I encourage you to see the next, the sequel of our story, and perhaps you'll be able to see where the Lair is in that one. The ingenue is Mary Pickford. She was well known for playing ingenue roles in the silent film era. The residence is the Davies Guest House, which is part of a park in Santa Monica. It was originally built sort of as a present by an extremely rich person for an actress named Marion Davies. It was just a small thing. It had 110 rooms. The picture actually is only of a guest house. The original, the real mansion was torn down in the 50s in order to put up a parking lot. The Spectre victims, in alphabetical order, and the hero of it all, naturally enough. If we have got a whole pile of published information, we are extremely unusual compared to most vendors in that we tell you how it works, and in sufficient detail. And you'll, as I said, there's 20-odd hours worth of video and a whole lot of other stuff available on the site. If you're looking for more details about Spectre itself, I recommend John Masters' paper, and it goes into considerable detail of explanation of many of the variations. And you can get it at there. A disclaimer, we're not security experts. We didn't foresee it. Serendipitous. It is easier to avoid things when things are simple. And sometimes you get lucky. We got lucky. Thank you. I do want to. Does somebody? Are there any questions on the Slido? If not, I'll take questions from the floor. Don't all speak at once.
The mill CPU, never heard of it, but what do you use it for? Like, is it general purpose? You have a target market?
The mill CPU is a general purpose CPU family, like the 360 was a family. There is a lower bound in terms of what the microarchitecture can do. It is basically a 64-bit machine. You could not do a 16-bit mill for various microarchitectural reasons. There is, at the high end of the family, the gold processor, which is probably the highest one that we will actually produce as a product, can issue 31 operations per cycle on an ongoing continuous basis. Again, that's the high end. The internal architecture, if you lift the hood, it looks like nothing you have ever seen. Anybody who's been in our videos knows what I'm talking about. And I encourage you to do. It's not a one-trick pony, and I can't just say, oh, well, it's because this. There's 20 hours of videos there. I encourage you to tackle them one by one in order. Okay?
Not speculative.
Not speculating ahead, indeed. Other questions, anyone? I love to brag about the baby, and if you want to buttonhole me, I'm more than happy to give you in all the depth you possibly want, any details that you desire. Thank you.